Good morning. I'm Brian Kloppenberg, and I'll be presenting a discussion about SIMTOI, which is a 5-dimensional GPU-accelerated general-purpose modeling tool for optical interferometry. Before I get started, though, I'd like to take a moment to thank Hal and Theo for letting me present my talk in this form rather than in person. As some of you may know, my wife and I are actually expecting our first child to be born actually this weekend. And given the uncertainty associated with when babies actually arrive, I thought it was probably a good idea to record my talk just in case, and fortunately Hal and Theo both agreed. So thank you very much for letting me do a video talk instead. Since the last CHARA conference, I left my postdoc position at Georgia State University and picked up a research scientist position at ArrayFire, which is a high-performance computing company located here in Atlanta. At ArrayFire, we specialize in solving both problems that are kind of regular sizes, like what we would encounter here in astronomy, and also big data problems using high-performance computing techniques, in particular CPU, GPU, and various accelerator programming. And just a plug for my company, just a couple of months ago we decided to open source our primary product, which used to cost $1,000. And now the ArrayFire library, which gives you very easy to use GPU acceleration, is available for free on GitHub, and you can also find it by going to arrayfire.com. So in the last couple of years, there's been a fairly large revolution which has happened within computing, and we've gone from a world in which we would have single-core CPUs to having multiple core CPUs, and then also a very different competing architecture called a graphical processing units. And here's kind of an overview of what you might expect to see between a CPU and a GPU. CPUs usually have a fairly small number of cores. The largest one on the market has 64 cores in it, and has a fairly low memory bandwidth, which means you can't transfer a lot of data back and forth between RAM and the processor. And they have a fairly low peak performance of about 0.2 teraflops. Compared with a GPU, which has an incredibly massive number of cores. Matter of fact, the NVIDIA K80 has almost 5,000 processors. They have a huge memory bandwidth because they're designed to push pixels around, and that's what you need for doing video games. And they have a very high performance of somewhere between 1 to 8 teraflops. So you can go from having a very easy to program device like a CPU to having a somewhat difficult program device like a GPU and easily pick up a factor of 10 or more in performance if you know actually how to work with these devices. Now SIMTOI is actually a program which takes advantage of GPU architecture in particular. So what is SIMTOI? SIMTOI is the simulation and modeling tool for optical interferometry. And if you've listened to many of my previous talks at these CHARA meetings, you probably already know a little bit about SIMTOI because this is one of the primary products that came out of my, my dissertation work. And SIMTOI is designed for sources whose Fourier transform is not easily computed. As you recall with Epsilon Aurigae, you had a star which had some limb darkening law, which we didn't know much about at the time, that was actually eclipsed by a disk whose actual orbital parameters and physical properties we didn't know anything about. And so it was almost impossible to write down all of the permutations of Fourier transforms that could be caused by having all these different combinations of limb darkening laws and disk parameters. And so I decided to go ahead and render the model out instead to an image and then use GPU computing to do all of the work. SIMTOI is also designed to combine multiple data sets of different data types. Right now, SIMTOI supports both interferometric and photometric data, but it would be relatively trivial to add astrometry and SED and a whole bunch of other different data types because of how SIMTOI is actually assembled under the hood. It's also designed for speed. When I render these models, I use OpenGL, which is the open graphics library. It's a computing graphics library used primarily in video games. And then I use OpenCL, which is the open compute language for doing high-performance GPU computing. To give you an example of how fast this is, using a 128 by 128 image with a sample OI-FITS file with over 2,300 UV points, I'm able to compute, to create the model, assemble it, and compute the corresponding interferometric data at about 450 of these iterations per second. So it's just blazingly fast. It's also designed for a high amount of computational accuracy because every single one of the backends that implements either interferometric or photometric data has unit tests to verify that the computations are actually correct. And it's also designed to be used and improved by the community. Unlike competing software like LitPro, SIMTOI is actually completely open source and distributed under a GPLv3 license, and all of the source code is available to you via the project, which is actually hosted on GitHub. So what can we model in SIMTOI? Now, if you've probably seen this before, you can model stars, which can be either spheres or they can be Roche surfaces or oblate spheroids. You can add stellar surface features. Example you see here on the right, you can see a spot, actually oblate star with a spot on it. You can model one of 7 different limb darkening laws, and you can also do gravity darkening, which you see here as this band across this oblate star, or as this darker region here on this Roche geometry. I also have support for several different disks. There's a hard edge cylinder, as we see here at the top. This is one of my disk models that came out of the Epsilon Origi paper. You can have power law density distributions, which can be, they can look somewhat like what you see here, kind of edge on. And then there's also a Pascusi and an Andrews disk model, which use real astrophysical density distributions, which are rendered here at the bottom. And you notice that the optical effects, as you would expect to see as you go to lower and lower densities, is rendered as having less and less darkness of you seeing here in the disks. You can also do time-dependent things like Keplerian orbits, solid body rotation, and in a yet unreleased version, I also have pulsation and support for nova ejecta. And there's also some really cool wavelength-dependent aspects that I built into SIMTOI in particular. At the bottom, you can see a picture of a 5,000 Kelvin star with power law limb darkening and a 4,500 Kelvin spot that's being rendered at either V-band, H-band, or N-band. And as you would expect, the spot actually becomes less contrasted compared to the surface as you move to the Rayleigh-Jeans portion of the blackbody radiation curve. SIMTOI also has support for several different minimization engines. In particular, there's an n-dimensional grid search algorithm, which if you so choose to use this, you can explore your chi-squared space at regular intervals. There's a least squares minimization fitting engine called LEVMAR, which implements the Levenberg-Marquardt algorithm. There's a Bayesian nested sampling minimization engine called MultiNest, which was written by Farron Farrows and Mike Hobson. And not only does this let you minimize to your data, but it also lets you test different hypotheses using Bayesian statistics. And finally, there is a bootstrapping minimization engine which uses LEVMAR under the hood, which allows you to derive realistic uncertainties from your interferometric and photometric data. However, if you decide to use this particular minimization engine, please read the documentation before using it. So let's do a quick demonstration of SIMTOI. What we're going to do is we're going to create a new model, which is going to consist of a spotted oblate star. We're going to add the model. We're going to show you a few things about the help that's built into SIMTOI within the GUI. Show you that there's a wavelength sliding ability, so you can change the wavelengths and see how things actually change in appearance with wavelengths, and animate the models. We're going to add some OI fits and photometric data and show you a couple of snapping features that allow you to pick a particular date or wavelength. Okay. So this is what SIMTOI would look like if you were to open it up for the first time. Everything is kind of grayed out, so you can't actually click on anything. From the File menu, you can choose a new model, you can save your model, or you can open an existing model. And after you have a model and some data loaded, you can also export the data to a text-based format so you can visualize it however you would like to choose. So let's go ahead and create a new model. We're going to have an image that's going to be 128 by 128 pixels wide, so it's 128 squared. And then the scale is going to be 0.05 milliarc seconds per pixel. Once we click the OK button, we notice that a whole bunch of the GUI elements are now no longer grayed out, so you can click on them. And the model region over here is actually black, which means that it's ready to actually render things. To add a model, we come down here to the lower left-hand corner and click the Add Model button. And here's an example of all the models that are actually built into SIMTOI already. What we're going to do is we're going to do an oblate star, so we're going to pick a Roche rotator. You can decide how you want the model to be positioned. You can either use a Keplerian orbit, which is a bound orbit. You can position it in terms of XY location, which is just going to be the classical northeast, just within the plane of the sky. Or you can also position a model three-dimensionally in terms of X, Y, and Z. I should also mention that the Keplerian orbit is also three-dimensional, but for all purposes, let's just pick the star to be just within the plane of the sky. You can choose one of several different limb darkening laws, so here's Claret, Field's, logarithmic power law, quadratic square root, and we're going to use a power law limb darkening star for here. And then finally, we can add features to the model. Presently, the only feature we have is a uniform spot, although I intend on adding Gaussian spots sometime soon. So we'll just click Add, shows up at the bottom, and we click OK. Alright, so on the left-hand side, now we see the parameters of the model as they're actually being picked from within SIMTOI. So we have a Roche rotator model which has a temperature of about 5,000. 5000 Kelvin. Now, if you didn't know what one of these particular parameters was actually supposed to be for, you can just hover your mouse over it and it'll bring up a tooltip help. So in this particular case, inclination is following the standard astronomical convention, and the value that you define in there is defined in terms of degrees. I'm going to go ahead and make the star just a little bit bigger. I'm going to make it have a polar radius of 2.5 milliarcseconds. And I know that SIMTOI actually renders things pole-on to begin with, so let's go ahead and put it so that it's edge-on. And just to show you that this is actually an oblate star, we're going to change the value of omega, which is the critical rotation rate, from about 0.5 to 0.9. And if you look to the right-hand side of the screen in the model area, you'll notice the model now versus now, and you can see that the star has grown much more oblate and gravity darkening is much more dramatic. Let's go ahead and put that back to where it was. Just wanted to show you that it actually can update in real time as you're pushing buttons. Okay, so let's go ahead and figure out where this spot is. If I remember right, if we move the spot to about 45 and make it just a little bit bigger, it'll be more apparent. You can see it right here in the lower right-hand corner of the star. And let's go ahead and show you some of the animation features that are built into SIMTOI. Let's give the star a 10-day rotation period, and then go ahead and start it animating at 0.1 days per tick. So it's going to increment the Julian date by 0.1 days at about every 70 milliseconds. It'll advance one step. We click the play button here, and now you can see that the star is actually being animated in the upper right-hand corner. The spot should just come around here in just a moment again. There it is. You might notice that the spot is actually a little bit pixelated. That's because of the heel pick subdivisions that we're actually using. We can make that a little bit smoother by increasing the number of subdivisions to 5. You notice that the spot is now a lot more round than what it was. With this animation widget down here in the bottom portion of the screen, you can step back by fractions of the rate. You can also step forward in time if you so choose, so you can make the star go whichever direction you would like it to go. And one other nice feature that's built into SIMTOI is this wavelength slider here. So you can see how the star would change in appearance from longer wavelengths to shorter wavelengths. So if we slide this back to optical wavelengths, you can see that the gravity darkening and also the spot become much more apparent, while they're producing much less flux. Or if you slide this all the way out to the far infrared out to about 100 microns, you can see that the contrast between the surface of the star and the spot decreases quite considerably. Alright, so let's add some data. Although this, I'm going to grab some data that I have for epsilon or IG. We're going to add 3 different OI fits files, and then we're also going to add some photometric data, the UBVRIJHK photometry. And you can see here that the data is actually loaded into this window up here at the top. The display includes the name of the file, the quantity of data. If you have interferometric data, you'll get the number of visibility points, T3 points, and differential visibility points if your data happens to have any. If you're dealing with photometric data, it'll just show you the total number of photometry points that are in the data set. Normally it shows the starting and ending Julian dates for the data file in all cases, but I made a change to the interferometric one that removed them just temporarily. You can see the mean Julian date of the file, which is actually when the modeling occurs. SIMTOI will use this, as well as, I should say, it'll use this in the case of the interferometric data. For the case of the photometric data, it'll look at every single photometric point independently. And there's also the mean wavelength of the file, which is actually calculated from the data. In the case of interferometric data, it's just the average wavelength of the unmasked data, or the data that's not flagged bad. In the case of photometric data, it usually corresponds to whatever the mean filter is. So here we have B band, which is about 0.445 microns. So a cool feature about SIMTOI is that if you want to go to a particular date and time, you can actually do that relatively easily. Let's say we want to pop back and forth between the dates that are in the 3 interferometric data sets here at the top. So we can click on them, and if you notice down here at the bottom of the screen, the date is automatically updated as we go back and forth. And the same goes for the photometric data. And we can also change the wavelength just by clicking on these entries that are up here. You notice the wavelength slider is going back and forth. Okay, so that's a quick demonstration of just the graphical elements within SIMTOI. The minimization engines are just here on the minimization tab, and all you do is you pick which one you'd like to use and you click the start button. They're not as configurable as what I'd like them to be, but that will soon change in the near future. Okay. Alright, so some other nice features about SIMTOI is that the save format is in the JavaScript object notation, or JSON format, which is a very commonly used format on the web. It's actually incredibly humanly readable, and I've documented how the file's actually structured on the wiki. You can script SIMTOI via command line arguments, and actually I did this for my dissertation work, and then also there's a young lady named Jana who's actually doing research, I believe using Vega data, that's been creating JSON files on the fly using Python and then feeding them into SIMTOI, and so she's completely able to modify her model however she'd like it to be. The repository for SIMTOI also contains some Python scripts for plotting the data and the SIMTOI results files, parsing the output from multinest, and interpreting bootstrap results. In the near future, there's going to be a couple of additional improvements that are going to be made. Ryan, who I believe is moderating this session, Fabian at least told me that he was going to be adding, Fabian told me that Ryan was going to be adding S-Atlas-based stellar limb darkening laws that were published in Hielding and Nielsen in 2011. Rob Parks and I are working on improving the documentation and usability. Fabian intends to add some additional minimization engines, and I'm kind of doing things that are under the hood. In particular, I'm working on creating packages for Linux, both in Debian RPM and TarGZ. I'm still working on doing integrated graphics support for Intel and AMD devices. It turns out there were some bugs in some of the display drivers that had to be fixed, and so I had to find workarounds to get these things to work. You might have noticed in SIMTOI there's actually this big gray area that's located here below the data region. That will be soon occupied by real-time plots that will show you the photometric or the interferometric data that's currently being evaluated, both the data as it was loaded from the file and also the data as is currently being compared, so that how the model is actually fitting to the data. Because of some work that I was doing at Arrayfire, I figured out a really interesting way to do obnoxiously fast photometry. And to give you an idea of how fast this would be, it would be about 15,000 photometric points per second, involving rendering the models out. Currently, SIMTOI only does about 200 of these per second, and so it'll lead to a considerable increase in the photometric simulation rate, permitting SIMTOI to potentially even do stellar spot modeling and light curve inversion. I intend to add some features to increase the rate at which we can simulate interferometric data, and then also add a new tessellation model for spheres. And if you're interested in helping out with SIMTOI, I do need some help getting Apple products working with SIMTOI. I believe it's going to be a relatively easy conversion to go from Qt4 to Qt5, and that's something that could probably be done in about a weekend if somebody has some experience with C and C++. And of course, I'm always looking for more users that would be willing to contribute some more documentation, demos, and how-to guides, because since I'm now partially out of astronomy, it's fairly difficult for me to work on the software and also do the documentation all at the same time. So where can you learn more about SIMTOI? You can check out SIMTOI via the SIMTOI repository, which is at github.com/bkloppenberg/SIMTOI. And there's also documentation that's located on the wiki, which is the same URL, just with wiki added to the end. Or you can ask one of the experienced SIMTOI users. You're more than welcome to email myself at brian@kloppenberg.net or discuss things with Fabian and Rob. So that's the conclusion of my talk, and with any luck, I'm actually available via Skype for about 2 minutes worth of questions. Thank you very much.